We said the format of any instruction is like this, that we have opcode and operands. The length of the opcode is 1 byte, and depending how we provide the operands in the instructions, the instruction length could be 1 byte, 2 bytes, or 3 bytes. And so far, we have given you the example of 1 byte and 2 byte instructions. As an example, we showed you the CMA and move AB, and we said in this case the operands are implied in the opcode. For example, if the opcode of this instruction is 78 in hexadecimal, by using just 1 byte, the CPU would understand that it needs to move the data from B register to the A register. It's just we call this addressing mode that we have registers, the register addressing mode. Or CMA is for complementing the contents in the A register. So the length of these two is just 1 byte. But sometimes you as the programmer need to provide 1 byte at the time to one of the registers. In this time, we need 1 byte for the opcode and 1 byte to send the as your data that you want to send to the destination registers, in this example the A register. So the instruction length would be 2 bytes, and we call the addressing mode immediate addressing mode. But let's say that you want to move 1 byte to the A register and or 1 byte to the B register and another byte to the C register. How would you do that? Well, you would say move I, B, and a byte. So in this example, let's say that you want to move the AA in hex to the B register. And you say move I, C, and BB in hex. Again, AA in hex means 1010 1010. You want to send these 8 bits of data to the B register and 1011 1011 to the C register. You have the option of doing this, and the length of these two instructions would be 2 bytes. So using 4 bytes, you could just finish this program. You just write, actually let me just write it in the RAM for you so you have a better understanding. Let's say these are 10, 11, 12, and 13 memory cells. In here, you'll just look at the manual of the 8085, the opcode for move IB, which is equal to 78. Actually, this was A and B. This is 78. The move I, the opcode of the move I, I'm just currently checking, it's 06. So the opcode for this would be 06. In 8085, ISR 06 is the opcode for move IB, and then you need to provide the next byte which you want to go to the B register, which is AA. So this would be AA. In the next memory cell, you want to write the opcode for move IC, which its opcode would be equal to 0E. So this is 0E. In the next lectures, we will explain how the opcode changes for that, what is the reason that the opcode for move IB is 06 and more for move IC is 0E, to give you a better understanding how you could resolve from the assembly code to the binary code. So next one would be the data that you want to provide for the C register, which is BB. So in this memory cell, you would write BB, and then the PC would point to this location. So the CPU would just retrieve the bytes and figures out that the next byte should go to either B or C register. And after the execution of these two instructions, we would have this value in the B register and this value in the C register. But you had a better option. A better option is provided in 8085 microprocessor for doing the same thing. And that is to say L, XI, B, and 2 bytes AA, BB in hex. But this instruction is saying that move AA to the B register and BB in the C register. This is a valid instruction of the 246 different instructions in the 8085 microprocessor. The length of this instruction is 1 byte for the opcode and 2 bytes for the data, and therefore the length of the instruction would be 3 bytes. So I want you to understand why we needed a 3 byte instruction. The opcode for LXI-B is equal to 0, 1. 0, 1 in hex is 0, 0, 0, 0, 0, 0, 0, 1. So if you want to program the same thing, you would say this. Let me just copy this so that I don't have to do it again. So you have this one. If you want to implement this program, what you say, let me just wipe this out. You would say that I need 0, 1 as the opcode of the instruction LXI. You would have 0, 1 in hex here. And then you have BB and AA. As we said, the lower byte comes first and in the lower address, and then the higher byte comes in the higher address. What the CPU would do in this case, while PC is pointing to the same location, it would retrieve this value and put it inside the IR register, and it would figure out that it needs to read the next byte and put it inside the C register, and then read the next byte after that and put it inside the B register. What is the difference with the previous program? In the previous program, the length of the whole program was 4 bytes, while in here the length of the program is 3 bytes. And understand that for every instruction, and here we did the same thing using 2 instructions, while here we did the thing with 1 instruction. And we know the execution of any instruction in any CPU has 3 phases: fetch, decode, and execute. So doing this in this way, not only the length of the program is shorter, but the execution of it would be faster. And that is the reason that we have a 3 bytes instructions in the 8085 microprocessor. But the addressing mode is still the same thing. We use the immediate addressing mode. Now I want to give you examples of other different addressing modes. But why would we need other addressing modes other than implied, register, and also immediate addressing mode? Let's say you want to move a value, this time from a register to memory. How would you do that? Well, the first case is to do this. As an example, let's say you want to move a value from a register to the address of 1000. Your goal is this: move the value from a register to the address of 1000 in the memory. The instruction in the 8085 to implement this is STA and then ADDR. We know that addresses in 8085 microprocessor are 2 bytes long. So this instruction would be 1 byte for the opcode of STA, which is 32 in hex, and 2 bytes for providing the address. So here we would have STA and an address equal to 1000. So the opcode would be 32 as the, well, in binary it would be 0011 0010. This would be the opcode, and then 2 bytes for the address. So it's say 00000000. This would be the 00 in hex. This is 32 in hex. And then you provide the 10, which is 0001 0000 here. This is 10 in hex. So this, as the programmer, you write this in the memory in 3 memory cells. What the CPU do is that it would fetch this value, put it inside the IR register as the opcode, while the PC was pointing to this location, and it would figure out that this instruction is saying that move the contents of the A register to the address, to the memory cell with the address that comes in the next 2 bytes. So first it would do the reading. So the first step was a fetch, right, to fetch the opcode. Then it would do a read of the next byte. So it would have a read, another read, which would be the read of the byte after that to complete the address that it wants to put on the address bus to choose the corresponding memory cell. So it would have another read, and then it needs to move the value from A register to the memory cell that has been chosen by the 16 bits here that has already been read and put on the address bus. So that is from the register to the memory by the CPU, which we call a write step. and this would be the execution of this. Don't worry about these things. Again, the steps would be explained. What do we mean by these things? I just wanted to give you what steps it would be taken by the CPU to execute such an instruction. So we call this addressing mode direct addressing mode. Why direct and why not calling it just immediate is because direct means that we provide the address of the memory directly. In the immediate addressing mode, the length of the instruction could be 2 bytes or 3 bytes. We could sometimes provide only 8 bits of data using something like this, or we could just provide 2 bytes of data to move in a register pair. But in this case, we want to provide address, and addresses are direct. You see, this 1000 doesn't go in any register. This 1000 that we name in this assembly code is an address for a memory cell that we want to move the contents from a register to that memory cell, and therefore we call the direct addressing mode.